So we will begin with this. Today we will understand keyboard networks. Keyboard networks will be learning today because this NPTEL course was conducted by Professor Kapasmi earlier, by Professor in the Department of Electrical Engineering of IIT Kharagpur. And some of his notes are available, so I'll be using to teach you about the concept of keyboard networks. So let us begin. We will consider a two-port network and they can have various parameters. So two-port network can be parameterized, can be characterized based on either short circuit admittance parameters, open circuit impedance parameters, hybrid parameters, or ABCD parameters. Right? So these are various parameters ways we can represent a two-port network. And these and it's the same two-port network. So because it's the same two-port network and we have various ways of characterizing them, there will be certain relation between these set of parameters. So we will consider relation between H and Y and Z parameters as well as a relation between H and Y parameters. We will look into it and try to understand it. Also, we will understand about reciprocal two-port networks. So when is a network reciprocal? So if the network is reciprocal, what would be the Y parameters and parameters? Right? This is typo here. It could be parameters. Similarly, for each that is considered for Y, Z, H, and T parameters. Similarly, the network was symmetrical, what would be the condition? That also we will look into today, and we will try to understand why. Right. So let us draw two-port network. B. There is the weekend session of network analysis, which is the problem solving and calculating session. The main thing which we are going to learn is about two-port networks. Two-port network. So this is the subject name is network analysis, and we will show a network which have two ports. We will look into the various parameters which can be used. Next, the Z parameter. Then there is the Y parameter. Next, the H parameters. And then there is the ABCD parameters. So these are the list of parameters which they have shown. Now we will draw a two-port network. We will draw a sample two-port network. We have two-port network. Okay? So this is a two-port network where there are two ports, like one set of ports are here, another set of ports are this side. And we apply voltage source plus minus V1, here plus minus V2. And you must note the current polarity. That is current I1, it is positive when it is flowing into the network. Okay. When the current I1 is flowing into the network, then the current I1 is positive. And in for the current I2, if it is flowing into the network, then it is positive. So this is a direction of positive current for I2, and this is a direction of positive current for I1. So whenever the current is flowing into the network, then we will consider that it is in positive direction. So that this convention you must keep in mind by solving these sums. And it might be in a sum, what they could do is they could just give you a random network, and to confuse you, they could write this is I2, and they could show the direction to be in the opposite direction. If such was the case, you might find the parameters, but there will be a negative sign of parameters. So and you get the wrong answer because it could also sign specific. So you have to be very careful while solving that, and you have to make sure that the direction of current as well as the direction of voltage are as required. Right? Just go back to the original configuration. That is, the direction of current must flow into the network, right? And it has no source and no internal source. So, yeah, they have also shown this is terminal 1, this terminal 1 prime, this is terminal 2, and this is terminal 2 prime. Alright, so these are the two terminals where the network is comes out, and we have connected a voltage source over there. Okay, so let us consider for y parameters what we have to do. Y parameters are basically admittance parameters. So in that we write the current I1 in terms of the voltages at the network, at the ports of the network. So I1 is written as equal to Y11 into V1 plus Y12 into V2. Similarly, we can write I2 to be equal to Y21 into V1 plus Y22 into V2. So these are the equations of the current, and they are represented in terms of the voltages of the port. As we observe, the dimension of these constants y11, y12, y21, y22, etc. They are in the dimension or the units of admittance. Okay, so that's why they have the units of admittance, and that's why it is known as admittance parameters. That's why y parameters are known as admittance parameters. And now we can represent them in the matrix format, which is compact. Okay, it's a compact way of representing these parameters. That is I1 upon I2 is equal to y11 into y12, y21 into y22. This multiplied by v1 and v1 and v2. Okay. So this is the matrix which relates the currents and the voltages. So usually what happens is for two-port network, we don't exactly know what is the network. Let's just assume we don't know the network. So what do we have to do in such a case is like it's like some a closed box. You assume that there's a closed box, and you are just given two ports which are coming out of it, and they tell you now you have to tell me what are the parameters of this network. So you'd have to conduct some sort of tests because you don't know what exactly is inside a network. So you conduct a set of tests and you will get some results. And based on the results of the test, you will say that you know some parameters of the two-port network. And using those parameters of the two-port network, you can use it for further purposes when we apply different inputs. Okay, so basically, you assume that you have a two-port network, but you don't know what is within the two-port network. Now you have to conduct some sort of tests. Once you conduct some tests on it, you get some parameters of the two-port network. After getting the parameters of the two-port network, you will know how the two-port network will respond if you change the input to the two-port network. So basically, we're trying to find out the characteristics of the two-port network. All right. So we let us look into it. What we can do to get it. So this is the two-port network. We have current I1 is flowing in, current I2 which is flowing in. We have connected this voltage source over here, V2 like this, across these terminals 2 and 2 prime, and this is 1 and 1 prime. All right. Now, what we do is we have to conduct some sort of test. So if we want to find out the Y parameters of the network, what we do is we short. Instead of a voltage source, we apply a short circuit over here. What does it mean is V1 becomes equal to 0. All right. So if V1 becomes equal to 0, what do we get is I1 will be equal to Y12 into V2. Okay, we know V2 when we measure I1 as well. Similarly, I2 will be equal to Y22 into V2. Okay, so from this, what we can get? We get Y12 is equal to V is equal to I1 on V2 with the condition that V1 is equal to 0. Similarly, get Y22 is equal to I2 upon V2 at the condition that V1 is equal to 0. Okay. So now we have found out Y12 and Y22. Now we want to find the other parameters of the network. So same what we will do is this two-port network is again given here. And now we will connect V1. V1, I1 also will be over here. And we will short V2. Okay, we will short V2. So what does this mean? V2 equal to 0. So now we get I1 to be equal to Y11 into V1 as well as I2 to be equal to Y21 into V1. So based on this, what do we get? We get Y11 is equal to I1 upon V1 in the condition that V2 equal to 0, that is the second port is short circuited. Similarly, Y21 is equal to I2 upon V1 with the same condition that V2 is equal to 0. Alright. So Neeraj, HP1, are you able to see the screen and everything, follow everything? Okay. So I've started teaching about two-port networks. That how is it does a two-port network look, and like this is how a two-port network looks. There are two voltage sources at each of the terminals of the network, and the current polarity should be positive while the current is flowing into the network. So that we must always keep in mind, right? Then I considered for admittance parameters, we represent the circuit as I1 is equal to Y11 V1 plus Y12 V2. I2 is equal to Y21 V1 plus Y22 V2. Then we write it in a compact form using matrices like this. And then we found out what was the driving point admittance, transfer admittance. Again, further the driving point admittance and transfer admittance. Okay. So any doubts still here? Or do you have any specific doubts which you can ask? Okay. Your mic is not working? Okay, we'll continue. So, see, there is the mic sort of option. So that you have to use to unmute. Right now you are muted. Or I can ask you to unmute. Are you able to unmute? Would you get a sort of option to unmute?
Good evening, sir.
So, okay, fine. So now I
Good
think
evening.
you have understood how to unmute and unmute. So you can be muted now. But when you have a doubt, you can unmute and you can ask me the doubt. All right.
Okay, sir. Can you hear me, sir?
Okay. So I'll continue. So now we will consider. So we did that for y parameters of the two-port network, and now we will do it for considering z parameters. So in the case of z parameters, we write it as we write in terms of the voltages. The voltages are written in terms of the current. V1 is equal to I1 into Z11 plus I2 into Z12, and V2 is equal to Z21 I1 plus Z22 into I2. So these are the equations for the Z parameters, and that we write it in matrix form as like this: V1 and V2. This is equal to Z11, Z12, Z21, and Z22 in terms of the currents I1 and I2. Right? So if you try to understand, it's the same two-port network, okay? there is this two-port network, that is assumed two-port network. There's this voltage source plus minus V1, I1 flowing in. Similarly, plus minus V2 and I2 which is flowing into the network. And these voltages and this current, these currents, they are represented in terms of these Z parameters, as well as we can represent in terms of Y parameters. Okay, so both set of parameters can be used to represent the same network. And if both set of parameters are used to represent the same network, then there should be some sort of relation between the two set of parameters. So you will observe this is I1, I2 in terms of V1 and V2. Similarly, in the next one, there is V1, V2 in terms of I1, I2. So we will write down, I'll write down the Y parameters. This is I1, this is I2, this is equal to Y11, Y12, Y21, and Y22 in terms of V1 and V2. So if you observe this matrix and this matrix, they are inverse of each other. If we will take the inverse of this matrix, we will get the matrix Z, right? So that is how these two parameters are related to each other. Okay. So any doubts still here? So now we can also need to find the parameters of the network using some sort of test. So usually, so like what you assume is you get a two-port network, you don't know anything about the two-port network. There's just some sort of black box. They just give you a box like this where you don't know what is inside this box. You just have one wire coming out over here, one wire coming out of here. Yeah. Yes, we can get one matrix from the other using matrix operation. So let me remove this one. Yeah. Okay. So this is one matrix V1, V like this is the Z matrix. So we will write it as V1, V2 is equal to the Z matrix into I1, I2. Okay. This entire matrix is known as the Z matrix. Alright. Similarly, this entire matrix is known as the Y matrix. So V1, V2 is equal to Z into I1, I2. Now let us assume we multiply this. Suppose this is equation A. We multiply both sides by Z inverse. We multiply both sides by Z inverse. So we get Z inverse V1, V2 is equal to Z inverse into Z into I1 into I2. So can you tell me what is Z inverse into Z? What is the value of Z inverse into Z? Unity matrix. Okay. So you will get a unity matrix you will get. So we will go to next page. So you get, so can you tell me, so this Z inverse Z, right? This Z inverse Z is a unity matrix 1, 0, 0, 1. Okay. And this is Z. So the left hand side is Z inverse V1, V2. And the right hand side is 1, 0, 0, 1 unity matrix into I1 into I2. So what will be the right hand side? Hmm? Yeah, it will be the current matrix I1, I2. Now we get the expression Z inverse V1 V2 is equal to I1 into I2. Now we interchange it. We write it as I1. We just take the left hand side to the right hand side and right hand side to the left hand side. So I1 into I2 is equal to Z inverse of V1 into V2. All right. Is this fine? This we got. Similarly, let us consider. Similarly, for the y parameters, we write it as I1, I2 is equal to y11, y12, y21 into y22 into v1 into v2. So this is B, this is C. So this we can write it as Y. Okay, the equivalent matrix Y. So if we compare B and C, what will we get? Neeraj, what will we get if we compare B and C? Yeah. So Y matrix is equal to Z inverse. So this property is very useful. Okay. Now, what happens? And we will actually be using this property in one sum which we'll be solving, last sum which we'll be solving. So we find the y parameters or we find the z parameters of a network. Then they tell us we find the y parameters. What should we again go to the elaborate steps and solve it? Or we can easily, instead of that, we can just take the z inverse of it. We find z, we take the inverse of that, we get the y matrix. Suppose we, so one more thing. Okay, so y is equal to z inverse of y is equal to z inverse. So what will be z in terms of y? Yeah. So we get z is equal to y inverse. Okay, and we will be using this one of these two while we'll be solving one of the example sums. So can you tell me, let us assume I have matrix A which have elements A, B, C, D. So what will be A inverse? How will we write A inverse? There's a shortcut formula. Can you tell me what is the shortcut formula? Okay. You don't know? I'll tell you. Okay. What is the determinant of this matrix? What is the determinant of this matrix say? The determinant is written in terms like this. So can you tell me what is the determinant of this matrix? So what is the determinant? Yeah, correct. The determinant of this matrix is A into D minus B into C. Right. Now, the A inverse matrix, there's a direct formula. What we have to do is, so this is a matrix with 2 rows, 2 columns. The inverse matrix will have how many rows and how many columns? Okay, same number of columns and same number of rows. You're correct. So the inverse matrix is written like this. Okay. This divided by this magnitude of A, by the determinant of A. What we do is A and D, the diagonal elements we just replace. Instead of A, we put D. Instead of A, we put replace it with D. And instead of D, we replace it by A. And instead of B, we replace it by minus B. And C, we replace by minus. That's all we have to do. So you might have studied this before, right? Like this is a very easy formula. Okay, okay. Don't worry. So the problem is we forget. Even I forget. So every time I have to Google and I have to remember this formula. So basically, you have to try to remain in touch. You have to try to keep practicing and keep on using these formulas. One way to like remember these formulas is every time you use it, you write it down. So you have one sum. In which you have to find the inverse of a 2 cross 2 matrix. You write down this formula, what will happen? And then you substitute those values of the matrix and you get a thing. But main thing is you write down the formula. So every time you write the formula, it gets into your head. More number of times you use it, less likely you're going to forget it. Okay. So will you be up? You're in which year of your BTech? You're doing BTech, right? Okay, okay, okay. Then you're trying to apply for GATE exam. You're preparing for GATE exam. Okay, okay. Yeah. So as you'll be trying to apply for GATE exam, you're preparing for GATE exam. So GATE exam is very competitive and you have to be very fast and you have to be fast and accurate. That is the goal. And so if you remember these formulas, it will be good. So you should be able to remember the relation between this parameters, that parameters, etc. How some parameters will help you to determine whether the circuit is reciprocal, symmetrical, or all that. And the main thing is what you must know it very well. That is the main goal. So uh, sometimes what we do is we solve some sums, and that time we know what we have done. But after some time we forget. As we said, you forget some formulas, it fades. But the goal in like gate exam and all that is you're not going to go there and derive any formula. There's no time for that. You have to know. Remember, if like this type of sum comes, I have to solve like this. This is the way. These are the steps. This step I have to follow. This step I have to follow. So that way you have to be fast and you have to know what you have to do exactly. So it is not. that difficult if you are fast and accurate. Okay, so that's why you have to remember the formulas. Now, yeah, it depends how much time you can get to remember it and all that, and it's up to you. But like one easy way is like once you solve a sum, you try to recollect how you solved it. What were the steps? What did you do? If you saw the question, what you thought you had to do, then you tried solving. In case you were not able to solve it, then you refer to the solution. From the solution, you found out what exactly they did. Then what you do is you close it and you try to solve it again on your own. When you solve it again on your own, where you were getting stuck, how exactly they did. And once you have solved it on your own, again you close the book and you try to recollect. Okay, first I did this step. I found out this parameter. Then I found out this voltage. Then I found out this current. Then I divided the current by the voltage or something like that. Then I got this. Then I got the power. Then I got the loss. Then I got the efficiency. So you should try to recollect in your mind what were the steps you followed for solving the sum. And when you do, so suppose you have solved a sum and you got a correct answer, then you refer to the solution and see if there is if they have used a shortcut method, if there's any direct formula which can be directly put, or whether they have found a more efficient way to get the answer. So those you have to try to incorporate while using. Okay. So those things you can keep in mind. Now we will get back to the topic. So we have these open circuit impedance parameters. So we represent the circuit in this format for impedance parameters. They written matrix form like this as we have done. Suppose we want to find Z11 and Z21. What we do is we apply a current source here I1 and we open this voltage source. Okay, if we open this, keep it open, what will happen? The current I2 will become zero. So when the current I2 becomes zero, we can get uh, what do you say? These driving point impedance of port one, the transfer impedance Z21, etc. So Z11 will be equal to V1 upon I1 when I2 is equal to zero. Similarly, Z21 will be equal to V2 upon I1 when I2 is equal to zero. So any doubts in this? Okay. So that's why, if you will remember, these are open circuit impedance parameters. When we like open circuit one side, one port, or we open circuit the other port, we can get the parameters of the network. Hmm. So that's what we have done. We have open circuit the secondary side, second side. We have got Z11 and Z21. We open circuit the port one, we got the parameters Z12 and Z22. So that's by open circuiting certain ports of the network, we are able to determine the parameters of the network. So that's why these are known as the open circuit impedance parameters. And if you'll observe, these parameters are the dimension of impedance. So what is the uh, SI unit of impedance? It will be ohm. Yeah, you're correct. Similarly, for these parameters, for Y parameters, we were shorting either port 2, we were shorting port 1, and because we were shorting it, we were able to find the admittance parameters. Okay. Okay, now we will look into this ABCD parameters and these parameters. So for these hybrid parameters, we represent V1, that is input V1 and output current I2. They are expressed in terms of the input current I1 and output voltage V2. That's why it is a hybrid mix of the open circuit parameters as well as the short circuit parameters. So we get it as V1 is equal to H11 into I1 plus H12 into V2. Similarly, I2 is equal to H21 into I1 plus H22 into V2. All right. Now, here also we write it in matrix form. V1 upon I2 is equal to H11, H12, H21, H22 into I1 into V2. So, what? So, can you tell me? Let us consider these equations for hybrid parameters. Hybrid parameters. We have V1 is equal to H11 I1 plus H12 V2. Similarly, I2 is equal to H21 into I1 plus H22 into V2. So can you tell me, how will I find H11? If I want to find H11, what I must do? If I want to find H11, what I must do? Yeah, you're correct. You have to short circuit the output side. So I get H11 to be equal to V1 upon I1 when V2 is equal to 0. That is output is short circuited. So what will be the dimension of H11? Yeah, it will be in ohm. Similarly, we found H11. What are the parameter we will find if we short circuit the second pole? We short circuit the output side. Yeah, we will find H11 and H21. Now, to find H12 and H22, what I must do? To find H12 and H22, what I must do? I will open circuit the input side. You're correct. So I will open circuit the input side. By open circuit the input side, then I will get H12 and H22. Okay. So let us assume we have H21 is equal to I2 upon I1 when V2 is equal to 0. So what is the dimension of H21? Yeah, it is dimensionless because it is the two quantities which have the same dimension are divided, so it is unitless. So what will be the dimension of H22? H22 is equal to I2 upon V2 when I1 is equal to 0. Yeah, to be ohm inverse only. So any doubts in this one? See, they have written H12, H21 are dimensionless, while H11 has dimension of impedance and H22 has dimension of admittance. Now we will consider ABCD parameters. Okay. What happens in ABCD parameters is this. We have V1, I1. They are represented in terms of A, B, C, D, V2 and minus of I2. Okay. This is how we represent them. Okay. See, the such parameters are useful for this small signal model of a BJT. Okay, they use these H parameters all that. ABCD parameters are useful for transmission lines. For transmission lines, when they try to characterize a transmission line, they use a pi model or they use a T model, etc. Such stuff. They use these ABCD parameters for the which act with them. Similarly, the admittance matrix Y, not exactly this two-port network, but something similar. Concept is used for load flow analysis. For power flow analysis, they use the Y admittance matrix. And that will be for a higher number of ports, etc. So that's why right now you are learning it on a small scale, very small network, etc. But they do find use in practical implementations. Okay. And another thing is you need it for getting marks. So port 1 is considered to be the sending end of the line and port 2 to be the receiving end of the line. Port 1 is to be excited from a generator, okay, whereas a load will be connected at port 2. Now, people dealing with transmission line will be interested to know the current delivered to a load from port 2. Yes, okay. This is where transmission lines, they use the ABCD parameters a lot. To be consistent with the convention, we use I2 flowing into the network as usual, which means the load current. But shown it properly. So this is the network with certain A, B, C, D parameters. Okay. This is plus minus V1. This is I1. And this is here you get V2 and I2. This is a normal convention. But for ABCD matrices, what do we consider is there's a generator over here, this side sending power, okay, and it generates a voltage V1 and it sends current I1. But over here at the output, there is a load connect. Okay, we'll consider this to be a load. And the current which is flowing into the load is minus I2. Okay, this current is flowing into the load. And when it flows into the load, it generates a voltage V2. It generates a voltage V2. Okay. So that is how this, so that's why the input voltage and currents, how they are related to the output voltage and currents. This is found using the ABCD parameters. Right? Now we will look further. So if you could tell me. So similarly, in a similar manner, we could either short the load, we could either open circuit the load, etc. If we do, we will be able to find the ABCD parameters of the network. Right, so that is similar as compared to all the previous cases which we have studied and which we have done. So I will not go into that. Now we have to find the relationship among y, z, h, and t parameters. Okay. So as I told, as we also discussed, the z parameters and y parameters are related to each other. We saw that y is equal to z inverse. Similarly, z is equal to y inverse. So that is one set of relation which we could directly observe, directly we could see, and it is a very simple and very useful relation which is being used. So, as we have considered over here, let us, and also that ABCD formula which I showed you. So, in case we wanted to find Z is y inverse. So, suppose y is equal to y11, y12, y21, y22. So, can you tell me what will be the determinant of y? Determinant of the y matrix. Yeah, this is the correct one, y11, y11 into y22 minus y21 into y1. So can you tell me what will be the matrix y inverse? This will be divided by the magnitude of y, that is y11 into y22 minus y21 into y12. So what will be over here? What will be the first element of this matrix? Will be y22, correct. And what will be the element over here, the last element of this matrix? Yeah, y11. What will be this element of the matrix? Yeah, minus y12. Then minus y12, correct. So we compare this with z, which is equal to z11, z12, z21, z22. We will get so Neeraj, actually, the Zoom meeting is only for 40 minutes, so I can join the meeting, right? So don't worry. That may happen again once more. So when once it happens, you'll have to again rejoin. Okay, I'll immediately start. So now we will see. Okay, you're able to see that screen, right? So from this, what will Z1, what will be the value of Z11 in terms of the Y parameter? Yeah, correct. Okay. Yeah. So similarly, we can get the other Z parameters in terms of the elements. So that's what they have shown over here also. Then they are considering, so that is the relation between the Z and Y matrices. Similarly, they will find the equations involving Y and H parameters. So this is Y parameters, this is the equation, and this for H parameters. Now, by simply doing matrix inversion, we will not get Y parameters in terms of H parameters. So what they will do is, they have to do algebraic manipulation. So this is I1. Okay, I1 is equal to Y11 V1 plus Y12 V2. So they write V1 in terms of I1 and V2. And when V1 is written in terms of I1 and V2, we get it in terms of H11 and H12. So we get H11 to be equal to 1 upon Y11, H1 to be 2 to be equal to minus Y12 upon Y11. Okay. Now they have in Y parameters I2 is equal to Y21 V1 plus Y22 into V2. This is there. But we also know that this V1, it can be written like this. V1 is equal to 1 upon Y11 I1 minus Y12 upon Y11 V2. So they substitute V1 over here and V2 they remain, let it be as it is. Then they get I2 in terms of I1 and V2. Once they get it in terms of I1 and V2, then they can compare it and it can be H21 will be equal to Y21 upon Y11. H22 will be equal to Y22 minus Y12 upon Y21 divided by Y1. So thus they have found out the relation between the H parameters and the Y parameters. So any doubts in this? Or I'll continue further. Okay. Now, yeah, very clear, very clear. Yeah, yes, as you said. Now we consider reciprocal two-port networks. So as they have said, now, okay, there are two types of reciprocity which they are showing. One is, okay, suppose we have a two-port network over here. Two-port network. This is V1 and this is short circuited. This is I1, I2, and this is I1. So if V1 upon I2, this is some ratio, let us assume it to be X. So I give an excitation over here V1 and I get a response at the other port, which is short circuit, I get a response I2. Similarly, there's another the same two-port network. I apply voltage source plus minus V2. Okay, I2 shows over here and I short this side and this is I1. And if I get V2 upon I1 to be equal to X, that is the ratio of the excitation and the output. Similarly, the ratio of excitation and the output remains the same, then that network is said to be reciprocal. Any doubts in this? Okay. I think I made a mistake. It actually should be ratio of excitation. I2 upon V1, ratio of excitation to input should be ratio of excitation to input. Okay. So this is for reciprocal network. And that's what they have told over here. So if I interchange the excitation and response, I get the same thing. Now, this is when I applied a voltage source. Suppose I applied a current source. There was a current source I1 over here. There is a two-port network over here. And I leave this open circuit. So this will be the response, this will be the input. So V2 upon I1. Okay, this is the response upon the excitation. This will be equal to X. Similarly, that is equal to V1 upon I2. Okay, this is at the condition where I2 is equal to 0. This is at the condition when I1 equal to 0. If this is valid, then we can say that the network is reciprocal. So either we could use this condition or we could use this condition to determine if the network is reciprocal. All right. So I'll proceed to the next step. Now they're saying they will apply the same concept and they will get. So, okay. Let us consider this in terms of the y parameters. If this was in terms of y parameters, we put I2 to be equal to V2 to be equal to 0. Okay, over here, V2 is equal to 0. So we know I2 is equal to y21 V1 plus y22 into V2. So we put V2 equal to 0. That means I2 upon V1 is equal to y21. So this is equal to y21. Similarly, over here, what do we have? We have V1 is equal to 0. This is V1 is equal to 0. If V1 is equal to 0, what do we get? We know I1 is equal to y11 V1 plus y112 into V2. Since this is equal to 0, so we get I1 upon V2 to be equal to y1. This to be equal to y1. So the network is supposed to be reciprocal. Y21 should be equal to y1. This is for y parameters. Okay. Any doubts in this? I hope not. So similarly, we can do it for open circuit parameters also, and you would get Z21 should be equal to Z12. This is for open circuit parameters. Right? And they have found that for H, for this H parameters, they have found that the relation should be H21 should be equal to minus H12. This should be the relation for H parameters. Similarly, the relation for this ABCD parameters, they have found it for it to be reciprocal, AD minus BC should be equal to 1. So they have summarized all which they have found, and they have found out that for the network to be reciprocal, Y12 should be equal to Y21 or it and Z12 should be equal to Z1 for either whatever parameters we consider. Similarly, H12 should be equal to minus H21 and AD minus BC should be equal to 1. So this is for reciprocal networks. So any doubts in reciprocal networks? Okay. Similarly, there's a case for symmetrical two-port networks. So in symmetrical two-port networks, what is the condition is that when I interchange the input and the output, okay, like suppose port 1 was the input, and then we make port 2 was the output. But then we change it like we make port 2 to be the input and port 1 to be the output. Then there will not be any change in the voltage and current at that port. If that is the case, then we say that the network is symmetrical. So what happens during that case? Let us see. This is my two-port network. Port 1, let us consider port 1 to be the input. Okay, this is V1, this is I1. And this is some port, some load V2 and I2. So this is the output port, this is the input port. So the ratio of V1, the input applied, and what the current we see, that is for this case, when port 1 is the input port. Similarly, suppose this the same two-port network. Now here, this is the load port and this is the input port. Okay, this is V2, this is I2, this is equal to I1, and here there will be some voltage V1 which will develop. So if the ratio of V2 upon I2, this is the input applied and the input current we see, this is supposed equal to X, this is also equal to X, then we say that the network is symmetrical. Okay, and if we know for Z parameters, V1 upon I1 can be found to be Z11. Similarly, V2 upon I2 will be found to be equal to Z22. Okay. If we see over here, we excite port 1 and we leave port 2 open. If we do that, then V1 upon I1 is equal to Z11. Similarly, when we excite port 2 and we keep port 1 open, we get V2 upon I2 is equal to Z22. So if the network is symmetric, then V1 upon I1 should be equal to V2 upon I2, or Z11 is equal to Z22. Alright. So any doubts on this? Similarly, for the H parameters, they have found it to be H11 into H22 minus H12 into H21 should be equal to 1. That means the determinant of the H parameters matrix should be equal to 1. Yeah. Here the case is opposite. Yeah, yes. Excitation is the numerator. I mean, if you notice, for Y parameters, when they do, port 1 is the input port, port 2 is the output port, and port 2 is shorted. Then, when port 2 is made the input port, then port 1 is shorted. So, what it means effectively is that the load, one port is the input port, the other port is the load port, that should have the same condition. Now, when we interchange the ports, when port 2 is made the input port and port 1 is made the output port, then port 1 also has to be shorted. Okay, so the load condition also should remain the same. Similarly, for when it is Z parameters also, we consider one port V1 is applied and the port 2 is open. And when we apply port 2 is the input, we apply V2 and then port 1 is open. Okay. So for symmetrical two-port network, for Y parameters, Y11 should be equal to Y22. For Z parameters, Z11 should be equal to Z22. If it is modeled using H parameters, then H11 into H22 minus H12 into H21 is equal to 1. And if it is modeled with T parameters, T parameters are known as the ABCD parameters as well. We will get A to be equal to A should be equal to D. Alright, we have considered symmetrical two-port networks. We have considered reciprocal two-port networks. We have considered various ways to represent networks and the relationship between these parameters H, Y, Z, and T parameters. And now we will go to solving the assignment. Okay, assignments. So till here, any doubt is there? If there's no doubt. I'll proceed with solving the assignment. Okay. Just consider. Okay, so this is the question, and we want to find the H parameters of the network. So we first will write the H parameters. So how do we write the H parameters? Is given by V1 is equal to H11 into I1 plus H12 into V2. Similarly, I2 is equal to H21 into I1 plus H22 into V2. This is for hybrid parameters. So we must know this relation very well. V1 is equal to H11 into I1 plus H12 into V2. Similarly, I2 is equal to H21 into I1 plus H22 into V2. Now we know this relation. Sorry. Now we will try solving this sum. So we know we apply KVL in this loop. Suppose we will apply KVL in this loop. What do we get? We will get V1 is equal to 3 into I1. Any doubts in this step? We got V1 is equal to 3 into I1. We just V1 because the voltage drop across this 3 ohm resistor, that is 3 into I1, and this is short circuited, and this goes again here. That's why V1 is equal to 3 I1. Now we compare this with this equation. So what will we get H11 to be equal to? Yeah. So in this circuit, when we applied KVL, we got it in terms of the V1. See, let us apply KVL in loop 1. So minus to plus, so V1 from this load, from this post, from here to here, so that it is in the direction of the current. That will be V1 minus 3 I1. Then from here to here, it is just wires. They have zero voltage drop. So V1 minus 3 I1 equal to 0. That's why we get V1 is equal to 3 into I1. So in comparison, we will get H11 is equal to 3 and H12 is equal to 0. Because this is 3I1 plus 0 into V2. So H12 is equal to 0, H11 is equal to 3. Alright. Then we will apply KCL at this node. Okay. At this node, what do we have? There is this current 0.2 V1 is coming in. 0.2 V1 is coming entering the node. I2 also is entering the node, that is plus I2. This is equal to, there's a current which is flowing out of the node. And that current which is flowing out of the node is equal to V2 upon 2. Like across this across this resistor, the potential is V2. Okay, so the current will be equal to V2 upon 2. Okay. So when we apply KCL at this node, we get 0.2 V1 entering plus I2 which is entering is equal to V2 upon 2, which is going out of the node. So we got 0.2 into V1 plus I2 equal to V2 upon 2. Now we know V1 is equal to 3 into I1, so we substitute over here. So we get 0.2 into 3 into I1 plus I2 is equal to 0.5 V2. So we get I2 to be equal to minus 0.6 I1 plus 0.5 V2. Comparing it with this equation, I2 is equal to H21 I1 plus H22 V2, we get H21 is equal to minus 0.6, H22 is equal to 0.5. So any doubts in this? Make it smaller so that you can see the entire screen. So any doubts in this? Okay. Good. Then we'll proceed to the next question. Okay. So we got it for this. Now we consider this network. Okay. So for this network, we need to take the screenshot from it. So this is the question we have. We have the relation between V1 is equal to 5 into V2 plus 8 I2 and I1 is equal to 6 into V2 plus 5 I2. Similarly, V2 and I2 also in terms of V3 and I3. Now we want to find the total relation. That is, see, if you notice, this is in terms of ABCD parameters. This also is in terms of ABCD parameters. Now you want to find the total relation between V1 I1 and V3 I3. So what we will do, wherever V2 is there, wherever V2 and I2 is there, we will substitute these equations. So we will get V1 is equal to 5 into V2. That is 5 into 5 V3 plus 7 into I3 plus 8 into I2. I2 is equal to 6 V3 plus 6 into I3. You ignore the ohm and inverse ohm. We get V1 is equal to 25 V3 plus 35 I3 plus 48 V3 plus 48 I3. So we get V1 is equal to 73 V3, 23 V3 plus 83 I3. This is equation A. Any doubts on how this is found? I hope you also are solving it simultaneously. So we will proceed. Okay, so we will proceed. We page So now we will substitute in this equation I1. I1 is equal to 6 into V2. That is equal to 6 into 5V3 plus 7 into I3 plus 5. Okay. 5 into 6V3 plus 6 into I3. That will be equal to I1 is equal to 30 into V3 plus 42, 42 I3 plus 30 into V3 plus 30 into I3. So we get I1 is equal to 60 into V3 plus 72 into I3. This is equation B. All right. So now we got equation A and equation B. And in the question they're asking, estimate Thevenin voltage seen from port 3. You want to find a Thevenin voltage. Thevenin voltage is known as the open circuit voltage. Also, we have been given that V1 is equal to 70 volts. So what we do is, open circuit voltage means what? I3 is equal to 0. If we substitute I3 equal to 0 over here, we get 70, that is the value of V1 is equal to 73 into V3, which will be the Thevenin voltage. So we get V Thevenin is equal to 70 upon 73, which comes out to be around equal to 0.959. 0.95, sorry, around 0.95. Let me write it over here. V Thevenin, it comes out to be 0.959 volts. Okay. So Neeraj, the calculators are allowed for gate exam. Okay. How many times you have given gate exam? This will be your first time. Okay. Then now we will consider, they have told us to find the Thevenin resistance and the Norton current. So if we want to find the Thevenin resistance, we first have to find the Norton current. So we'll first solve this. Okay, so what we have to do is Norton current. If we have to do Norton current, that means we have to short this port. If we short this port means V3 equal to 0. So what we do in this equation, we have to put V3 equal to 0. So if we put V3 equal to 0, then what we get? Okay, this be okay. We have to put V3 equal to 0. So over here, when we put V3 equal to 0, we get V1, that is 70, is equal to 83 into I3. Okay, 70 is equal to 83 into I3. So I get I3 is equal to 70 upon 80, 70 upon 83, which value comes out to be 0.84 ampere. Okay, it comes out to be 0.84 ampere. This is the Norton current. Now we want to find the Thevenin resistance. That will be V Thevenin upon I Norton. That will be equal to 70 upon 73 divided by 70 upon 83. That will be equal to 83 upon 73, which value comes out to be around 1.13. Comes out to be 1.13. So, any doubts in this sum? Okay, so I'll continue. This will be in ohms. Yeah. Okay. And just you have to remember, like for Thevenin's, you have to find the open circuit voltage. For Norton's, you have to find the short circuit current. And the Thevenin's resistance is equal to the Thevenin's voltage divided by the Norton's current. That is all you have to do. Okay. Now we'll proceed to the next question. We have this. This is the equation. Okay, this is the circuit. Also, the meeting will end in 8 minutes, in some 7 minutes or something. After 10, we again join. I'll again start the session for a short time. So, this is the network. This is the question. So this is the network. V1 is here, I1 is here, V2 is here, I2 is here. So what will be the current through this branch? Can you tell me what will be the current through this branch? Yeah, correct. It will be I1 plus I2. So let us apply KVL in loop 1. Okay. We get V1 minus 3 into I1, that is the drop across this, minus 3 into I1 plus I2 is equal to 0. So we get, when we solve it, we get V1 is equal to 6 into I1 plus 3 into I2. This is equation A. And we know for Z parameters, it is V1 is equal to Z11 into I1 plus Z12 into I2. Similarly, V2 is equal to Z21 into I1 plus Z22 into I2. So on comparing this with equation A with this equation, we get Z11 should be equal to 6 ohm and Z12 is equal to 3 ohm. Any doubts in this? Okay, fine. Now we'll apply KVL in loop 2. We will apply this, right? KVL in loop 2. We get minus to plus, that is V2 plus to minus. So that is minus 2V1 and it is in the correct, so it is minus 5 into I2 minus 3, the drop into I1 plus I2, that is I1 plus I2 is equal to 0. So we get V2 is equal to 2 into V1 plus 3 into I1 plus 8 into I2. Okay, this is by simple algebraic manipulation. It will be simple now, but when you go and solve the sum on your own, there you will make mistakes. Okay, that's why you must be very careful when doing it. Here, you should not always directly go for shortcuts. Once you have developed good confidence and you have solved many sums, you know where you make mistakes and you are careful and the areas where you make mistakes, then you can start going for shorter techniques. But till then, you try to go for the long way. Now, V1 we know is 6 into I1 plus 3 into I2. So we get V2 is equal to 2 into 6 into I1 plus 3 into I2 plus 3 into I1 plus 8 into I2. So we get V2 to be equal to 12 into I1 plus 6 into I2 plus 3 into I1 plus 8 into I2. So we get V2 to be equal to 15 into I1 plus 14 into I2. This is equation B. When we compare this equation with this equation, V2 is equal to Z21 I1 plus Z22 I2, we get Z21 to be equal to 15 ohm and Z22 to be equal to 14 ohm. All right. So that's how we have solved these sums very fast. Okay. This just we have to know, we have to just apply simple KVL. You have to just know the equations relating the voltages and currents in terms of the required parameters. Till now we did for Y parameters and Z parameters. And one was for ABCD parameters, but and it was a cascaded network which we were easily able to solve. Now we will proceed to the next question. Okay. I'll paste this here. So this is the question. So we will assume, oops. So can you tell me? We will assume there's this current like this. There is another current like this, and there is a current like this. This current is Ix. This current is I1. This current is I2. So can you tell me what is the current through the 3 ohm resistor? Through the 3 ohm resistor, what is the current flowing through the 3 ohm resistor? Okay, this meeting will stop in 1 minute. After that, I'll again resume the meeting. Okay. Current through the 3 ohm resistor I1 minus I. So you are correct. Correct. Similarly, what is the current through the 6 ohm resistor? Okay. So Neeraj, now we have found the current through the 6 ohm resistor, current through 3 ohm resistor we know. Current through the 8 ohm resistor is Ix. What will be the current through the 2 ohm resistor then? That will be I1 plus I2. Okay. Yeah. So now we are ready to apply KVL. So what we do is apply KVL in loop 1. We apply KVL in this loop. What will we get when we apply KVL in the loop? See, because when we apply KVL in this loop, we will get minus to plus, so V1 minus this 3 into the current through this I1 minus Ix. So 3 into I1 minus Ix Then minus 2 into I1 plus I2, minus 2 into I1 plus I2, this is equal to 0. So what do we get? We will get V1 will be equal to 5 into I1 plus 2 into I2 minus 3 into Ix. This is equation A. Any doubts in this? Okay, so now we will apply KVL in this loop. We will apply KVL in this loop. We will get V2 minus 6 into I2 plus Ix minus 2 into I1 plus I2. This is equal to 0. So we will get V2 to be equal to 2 into I1 plus 8 into I2 plus 6 into Ix. This is B. So thus we have found V1, V2 in terms of I1, I2, Ix. But we want V1 and V2 to be in terms of I1 into I2. In terms of I1 and I2. Because then only we can find the Z parameter. So now we will apply KVL in the loop 3. When we apply KVL in loop 3, what we get is minus 8 into Ix, because it's a drop across the resistor, and this drop across this 6 ohm resistor is minus 6 into Ix plus I2 minus 3 into this Ix minus I1. Ix minus I1 is equal to 0. So when we simplify, what is there is minus, minus, minus. So we can make it as plus, 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 plus. We get 17 Ix plus 6 into I2 minus 3 into I1 is equal to 0. Or Ix is equal to 3 I1 upon 17 minus 6 I2 upon 17. Alright? Any doubts in this? Okay. So now we will substitute this value of Ix in A and B. When we substitute it, we get V1 is equal to 5 into I1 plus 2 into I2 minus 3 into Ix. 3 into this one. 3 I1 upon 17 minus 6 I2 upon 17. This will be equal to 5 into I1 plus 2 into I2 minus 9 I1 upon 17 plus 18 I2 upon 17. When you solve it, you get V1 is equal to 17 into 5 is 85 minus 9 is 76. 76 I1 upon 17 plus 2 into 17 is 34 plus 18 is 52 plus 52 upon 17 I2. This we get V1 in terms of I1 and I2. Alright. Similarly, we substitute this Ix in this equation B, we get V2 is equal to 2 into I1 plus 8 into I2 plus 6 into Ix, that is plus 6 into 3 into I1 upon 17 minus 6 into I2 upon 17. So we get it as equal to 2 into I1 plus 8 into I2 plus 18 into I1 upon 17 minus 36 into I2 upon 17. So we get V2 is equal to 2 into 17 is 34 plus 18, that is equal to 52. So it becomes 52 upon 17 I1 plus 8 into 17. What is 8 into 7? 85 plus 34. 85 plus 51. that is equal to 86. 136 minus 36, that is 100. It becomes 100 upon 17 into I4. This is equation E. When we compare B's with the equation B1 is equal to Z11 I1 plus Z12 I2, and B2 is equal to Z21 I1 plus Z22 into I2, we will get Z11 is equal to 76 upon 17, Z12 is equal to 52 upon 17, Z21 is equal to 52 upon 17, and Z22 is equal to 100 upon 17. So any doubts in this? So, oh, very nice. So we'll write the Z matrix. Z matrix is Z11, Z12, Z21, Z22, that is equal to 76 upon 17, 52 upon 17, 52 upon 17, and 100 upon 17. So can you tell me what is the determinant of Z? Yeah, the mathematical value. Yeah, correct. So we get this equal to 16.941. Yeah. Now we want to find the Y matrix. If you remember, Y matrix is equal to Z inverse. So can you find the Y matrix? What will this be? This will be divided by the mod of Z. So what will be over here? Yeah, this will be 100 upon 17. This will be 76 upon 17. This will be minus 52 upon 17. And this will be minus 52 upon 17. Okay. So if you calculate what you will get the required values. So can you calculate and tell what will be the value of Y11? Yes. Y11 you get it to be 0.347. Similarly, Y12 you get it to be minus 0.1805. Y21 also you get it to be minus 0.1805. Y22 we get it to be equal to 0.2638. Y22 is equal to 0.2638. So can you tell me, is this network reciprocal? Is this a reciprocal network? Yeah, it is a reciprocal network. Is it a symmetrical network? Why? Why it's not symmetrical? Okay, yeah. If it has to be symmetrical, Y11 should be equal to Y22. So which is not happening. So we know, we have found out the network is reciprocal, but the network is not symmetrical. Okay. So Neeraj, any doubts you have from what you have done today? Anything which you're struggling, finding difficult? So I'll just do a brief recap. You know, this was the first sum. We applied KVL over here. V1 is equal to 3I1. We applied KCL over here. The current over here is V2 upon 2, because the potential at this point is plus V2 and the potential at this point is minus. It's at ground. The potential between this node and this node is V2. So the current is equal to V2 upon 2. The current is flowing out. So V2 upon 2 is equal to 0.2 V1 plus I2. And based on the equation for H parameters, that is V1 equal to H11 I1 plus H12 V2, and I2 is equal to H21 I1 plus H22 V2. We solved it and we got H11, we got H12, we got H21, H22 we found. Okay, the dimensions you must keep it in mind. Similarly, this is a two-port network, one, two-port network two, and they are connected in cascade. And we have this relation between V1 I1 and V2 I2. Similarly, the relation between V2 I2 and V3 I3. So what we did is we found a total equivalent relation between V1 I1 and V3 I3. Once we found a total equivalent relation, what we did, we had to find a Thevenin's voltage. So for Thevenin's voltage, what we did, we made I3 to be equal to 0. After making I3 to be equal to 0, we found the voltage V3 over there. Okay, so that is the Thevenin's voltage. Similarly, then we had to find a Thevenin's resistance. To find a Thevenin's resistance, first we need to find a Norton's current. So to find the Norton's current, what we did was we shorted this. We shorted this means V3 equal to 0. So when we have V3 equal to 0, we get some Norton's current I3, that is equal to IN, and then the Thevenin's resistance is equal to V Thevenin divided by Norton's current. So that we found out. So that's why I'm saying once you do the sum, you go through it. You try to remember what you did, how you did it. Okay, so that you must try to revise and keep it in mind. That's why I'm trying to recollect. Similarly, in this circuit, you have to find your Z parameters. we know this is I1, this is I2. So the current through this resistor should be equal to I1 plus I2. Keeping that in mind, we found KVL of this loop, KVL of this loop as well. We found V1 in terms of I1, I2, and directly we got Z11, Z12. In this one, we got V2 in terms of I2, I1, and V1. And the values of V1, which we found over here, we substituted that. And then we got V2 in terms of I2 and I1 alone. And once we got that, we found the Z parameters Z21 and Z22. So this also was a very simple. Then we come to this network, which is a bit complicated. But over here again, what we did was we did mesh analysis again, and we drew the currents I1, I2, Ix, found out what current is flowing to 3 ohm, what current is flowing to 2 ohm, to 6 ohm, etc. And using that, we applied KVL in this mesh 1, this mesh 2, this mesh 3. Then we got V1, V2 in terms of I1, I2 by substituting the value of Ix, which we got. And then we got the Z matrix. Okay, we got the Z matrix. Then we found the determinant of the Z matrix. And then we found the inverse of the Z matrix. That turns out to be the Y matrix. Okay, that is a simple thing which we did, and we use that shortcut. This gets interchanged, these two get interchanged, and for this we just add a negative sign. Just add a negative sign. This is valid only for a 2 cross 2 matrix, right? For 3 cross 3, it becomes a bit complicated enough. So this is the case. And then we found out the Y parameters, Y11, Y12, Y21, Y22, etc. Then for the network to be reciprocal, we know that Y12 should be equal to Y21. That is, we know Y12 should be equal to Y21. For the network to be symmetric, Y11 should be equal to Y22, which does not happen over here. That is why we say it is not symmetrical. Okay. So, any doubts in this? So, if there are no doubts, we'll end this session. Okay. So, this session is conducted every Monday from 6 to 8 p.m., 6 p.m. to 8 p.m. And next week, we will be solving assignment 11. All right. Diagram for first question. Yeah. This is the diagram for the first question. Yeah. So, yeah, for second loop equation. We did not find the second loop equation. Here we found the node equation we found. Yeah. Okay. So, what is the doubt there? It has it has an impact, right? We are considering it. Yeah. Yeah, it is in parallel with the 2 ohm, but we are considering the effect. We are finding KCL at this node. Okay. We are finding KCL over here. Let me go to this. We are finding KCL at this node. Yes, at this node. The current entering this node is 0.21, 0.2 into V1, which is given by the dependent current source, plus I2 also which is entering, which is equal to the current leaving, that is V2 upon 2. So that's how this dependent source also is having an effect. Okay. Any other doubts? Okay, so I'll end this session. So thank you for joining. Please join next week. Bye.